Hi, and welcome to Colu Math. Today we're going to be looking at permutations. Let's look at a quick textbook definition. An arrangement where order matters. Well, that's not particularly helpful. Your textbook might also have this. NPR equals N exclamation mark over N minus R exclamation mark. Not particularly helpful either. Well, let's take a look at an example, and we'll see if that helps clear up some of this. Your town has a bike race every year, and this year you're going to be racing in it. But you're going to be borrowing your friend's bike, and he's left it chained up for you on a light post downtown. And you take a look at the lock, and you realize you've forgotten what the combination was. So you take a look on the other side, and it appears there's another lock. And you don't know what that combination is either. So, well, you need to get this bike out, and we're going to have to, guess the combination. And the question would be, considering these two different locks, if we're going to have to guess the code, which lock would take less tries to go through all the possibilities? Which lock has the fewest possible permutations? Well, let's try to figure that out. Okay, so if we look at the first lock here, we know that there's 5 possible digits in the combination, right? There's 5 different wheels, and each of those wheels is numbered 1 through 8. Okay, so I guess what we could do is actually go over to the blackboard here and actually write out each of those possible permutations. We could do 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 3, 1, 1, well, we could do that and go ahead and through that process, and that would certainly work. But if we notice here, the blackboard is filling up, and we're still in the 114 range here. So we're going to have to find a quicker way to figure that out. But maybe if we hop over to the other lock, that'll be a little easier for us to figure out. Okay, so these are the old combination locks, and there's 3 numbers in each of these combinations, and each of those numbers could be between 0 and 39. So each of those has those options. So we could, all right, I guess back to the blackboard. So if we take a look at the blackboard here, we could have a 0, 0, 0, a 0, 0, 1, a 0, 0, 2, a 0, 0, 3, and, well, seems like there's a lot of them. More than I'm willing to write out, and let's face it, if this is ever going to be on a test, we're going to have to get to the end of the test before the bell rings, and if I'll be writing this much information out, I'm going to be in some trouble. So, well, let's take a look at the this lock here and see if we can make this question a little bit easier to figure out. Let's take out 3 of those wheels and look at a simpler lock here with only 2 possible digits. So we can get rid of that extra information there. So this one we could actually chart out on the blackboard. It wouldn't actually be too bad. So let's get started on that. 1, 1, 1, 2, 1, 3. And keep in mind that first number there is indicating the first number in the combination, and the second number there is the second number. So you can see we've listed out all the possible combinations there. If you notice, we have, well, how many do we have? Let's see, if we have 8 columns and we have 8 rows, we can multiply those together, and that tells us we have 64 possible permutations. Well, okay, that wasn't so bad. But of course, that was a lot easier than the problem we were looking at. But I wonder if we could take that same idea and extract it out to the bigger lock. So when we were looking at the smaller lock here and we written them out on the board, we realized that we'd made columns and rows made of our different possible outcomes. So in fact, we had 8 columns and 8 rows. Maybe we could just multiply those values together to get 64 instead of having to write them all out. And we can actually use that same ideology on the tougher lock. So when we go back to having 5 possible digits, each with a wheel numbered 1 through 8, we know that we actually can look at the possible options for each of those possible digits. And we have 8 for each of those. We multiply those all together. 32,768 possible permutations. And we can apply the same thought process to the other lock. Here we had 3 numbers in the combination, and each number could be between 0 and 39. So if we look at the possibilities for each of those numbers, there are 40 possibilities. We multiply those 3 numbers together for the 3 different numbers in the combination, and that tells us we have 64,000 possible permutations. And if we compare the two together, we can see that the lock with the fewest possible permutations is the one on the left. And in fact, half of the possible permutations of the lock on the right. So if we guess with the lock on the left, we'll have far fewer guesses to make. And in fact, our friend is not so smart, and his combination was 1, 1, 1, 1, 1, so we guessed it on the first try. So we managed to make it to the race on time, and well, there you are back there in the race, all ready to go. And the prizes for the race are awarded for first, second, and third place. The question arises, how many different arrangements of first, second, and third place can be made from the racers in the race? Or how many permutations for the top 3 spots? Well, let's take a look. How many racers do we have here? 1, 2, 3. Well, let's just say 99. Let's just do 99 instead of counting there. So there are 99 racers total. And, well, I guess we could probably put 99 into each spot there and multiply that. Probably makes sense. Wait a minute, does this make sense? Well, I don't know. We should probably take a look at it. So there's our 99 racers, and they're all at the finish line waiting for the prizes to be handed out. And there's only going to be a prize for first, second, and third. So the first person is announced, and that's our third place winner. So if you notice, we had 99 racers in contention for third place, but now one of them is already occupying third place. So we only have 98 racers in contention for second place. So one of those is selected because he got second place, and that only leaves us 97 racers to select from. So when we calculate our selections here, we can't just use 99 repeatedly because the situation changes. Somebody gets first place, well, there's only 98 racers looking for second. And if somebody gets second, well, then there's only 97 racers looking for third. So instead of 99 times 99 times 99, we're actually going to count down from 99. Because the first time there's 99 possible, if somebody crosses the finish line, there's 98 people still on the race. Somebody crosses the finish line, there's still 97 people out there possible for third place. We multiply those together, and that gets us 941,094 different possible outcomes for first, second, or third. So let's look back at the textbook definitions here. And there's our NPR again. And the textbook tells us that's the number of permutations that can be made from n items when we select R. And there's that formula again. Now, what exactly is that exclamation mark? That exclamation mark is what we call a factorial. And a factorial is, so we have the number n there as a factorial. It's the product of all the integers. Remember, that's the whole numbers there that can be positive or negative, from n down to 1. So let's look at an example here, and maybe this will help us take a look. So we've got a 5 factorial there. Remember, the factorial is the product of all the integers from n down to 1. So our first integer is going to be 5, and we're going to count down to 1. So 5, 4, 3, 2, 1, and we're going to multiply those because it's the product. And that's going to give us 120. Okay, so maybe this isn't so bad at all. And if we look at some of the first few factorials, you can see how the pattern goes. And that's the factorial. You start with the n value, you count down to 1, and you multiply all those numbers together. Okay, so just to make things easier here, why don't we just focus on these first 9 racers here so we can see these calculations at work. So if we have those 9 racers, we have 9 possible ones. The first one crosses the finish line, there's 8 left. Second one crosses the finish line, there's 7 left. And we can multiply those values together to get a value of 504 different possible outcomes for first, second, or third, when there's only 9 racers. You can see the drastic difference there between 9 and 99. So let's use the permutation formula here. NPR stands for the number of permutations that can be made from n items selecting R. Well, in this case, we had 9 racers, and we were selecting the top 3. Okay, cool. So let's go ahead and plug it into that equation. So that's not too hard. Let's do the parentheses first. 9 minus 3 is 6 on the bottom. So we have 9 factorial over 6 factorial, and we can plug those both into our calculator. That gives us 362,880 over 720. When we divide that out, sure enough, we get 504. Just like we saw last time with our calculation. So we know we're doing the right thing. Take a look at this too. This is kind of interesting. If we actually expand these out in what we call a factorial expansion, so you can see all the numbers that multiply together, remember the rules of division, and we can actually cancel out the duplications we have here. So we can actually cancel out these numbers all the way from 1 to 6 on the top and bottom, And that leaves us with 9 times 8 times 7, which is the exact calculation we made the first time we set it up. Pretty neat, huh?
Wait a minute, sir.
Hey Joe, how you doing?
Sir, could we try this with the previous lock question? Because I went ahead and calculated it, and 8 chose 2 is actually 56, which is not what we had before. So, does this even work?
Really cool, Joe. You actually came across something there. It turns out that there are 2 different types of permutations. On the left here, we have the combination locks. And on the right, we have the race candidates, where several are selected there as winners and losers, quite frankly. So on the right-hand side, because we had that changing situation where people were selected, the selections depend on the other selections, okay? Think about that. If you get first place, you can't be chosen for second place. And if you get third place, well, you couldn't have been chosen for first place. So it depends who gets selected for which position. On the left-hand side, the combination locks, the selections do not depend on the other selections. You could have 5 twice in a row, or you could have 3, 4 times in a row. The selections do not depend on the others. And if you think about it like probability back in our previous videos, you could almost think of the events on the left here as independent and the ones on the right here as dependent. Because on the left, the selections are independent of one another. It doesn't matter, you can have the same selection 5 times. On the right-hand side, it's dependent. You can only be in one of the places at one at a time. Of course, don't use these terms around your teacher because she'll think you're crazy, because I've never seen anyone use these terms, but it's a pretty good way to separate them out. So those independent permutations on the left-hand side, they're the ones that do not depend on the other selection. Those are calculated with what we call the counting principle. And the counting principle is when you make spaces for each of the selections you make, and you fill them up with the number of possible selections for each of those and multiply them together. That's the counting principle, okay? Those dependent permutations you solve with the NPR, okay? And so you use that equation and you plug them in. Actually, I'm going to show you guys a little trick here for the NPR formula. Okay, if you remember when we calculated 9p3 and we crossed out the duplicates on the top and bottom of the fraction, that left us with 987. And actually, if you notice, that's only 3 numbers, the same 3 that's sitting next to our p there. So what we can do is actually come up with a little shortcut for calculating permutations that I used to teach my students that they really seem to like. It basically works like this. To calculate NPR, you make the number r into the number of spaces. So if you have 3 as the number for r, you'd make 3 spaces. If you had 10 for the number for r, you'd make 10 spaces. Multiply those all together. And then you're going to start with n in the first spot, and you're going to count down from n until you've filled up all the spots. Multiply those together, and you have your permutation, your number of permutations. Let's take a look at an example. So 7p3, we'd have 3 spaces because r is the number of spaces, and we'd start with 7 and count down for each one, so 7, 6, and 5, and multiply them together. If we had 6p4, we'd have 4 spaces because r is 4, and we'd start with 6 and count down to fill up the spaces and multiply them all together. If we had 8p7, we would have 7 spaces, and we'd start with 8, count down, and multiply those all together once we filled up the spaces. It's a nice kind of simple way to do permutations that maybe you haven't seen before. Next time, we'll be looking at combinations, and it's going to be pretty simple after all this. Okay, so see you guys next time.